Welcome to the second phase of the introductory part of heterogeneous polymerization. Now, in the previous lecture, we discussed about the basic concept of heterogeneous polymerization. We discussed about the precipitation polymerization. Then we started the suspension polymerization, and we discussed the various aspects attributed to the suspension polymerization. Now, let's have a look about the bead suspension polymerization. The bead suspension polymerization process, the bead form of suspension polymerization, and the polymer is soluble in its monomer. Therefore, the monomer polymer mixture is usually termed as homogeneous one. So, in that case, the suspension system may be viewed as an aqueous dispersion of a time varying viscoelastic fluid. So, this offers a usefulness of this particular polymerization process. So, polystyrene which is used in the injection molding is manufactured by the suspension bead process. Polymethyl methacrylate and its copolymer usually containing small quantity of acrylate esters, they are also produced by the bead suspension process. So, in the case of styrene acrylonitrile copolymer, the process of choice of batch suspension polymerization is typically one involving say sometimes azeotropic monomer, sometimes co-monomer formulation to mitigate the compositional drift. So, this is again an important factor which need to be addressed while we are discussing this bead suspension polymerization. Now, the problem also occur because in continuous aqueous process, significantly more acrylonitrile than styrene being dissolved in due course of time. So, as the conversion proceeds, the acrylonitrile diffuses into the polymer particles and the ratio of monomer in the bead varies, thereby creating a difference in the structure of a copolymer. So, sometimes it is feasible and sometimes it is highly you can say the undesirable one. Now, the high impact polystyrene and acrylonitrile butadiene styrene copolymer, they are often prepared in combined bulk suspension process. So, this usually begins with a solution of a polybutadiene in the styrene or styrene acrylonitrile. Now, subsequently the polymerization of styrene or styrene acrylonitrile is initiated and continues under the stirring until the phase inversion occurs. So, that is the turning point for this polymerization process. Now, in the final stage, water and dispersants are added to the system with the quite obvious reason, and the polymerization is completed in suspension. Sometimes this can be utilized in expendable polystyrene production. Now, this EPS or expendable polystyrene is manufactured by the suspension polymerization in the presence of a blowing agent. One of the foremost blowing agent is pentane. So, it is also possible to inject the blowing agent to the polymer after the polymerization and allowing it to diffuse into the beads. So, sometimes you may have a previous one and sometimes you may inject afterward. So, this depends on the suitability of the process. The appropriate volume of deionized water is usually initially charged to the reactor at ambient temperature, and thereby you can begin the agitation. So, this is the initial protocol of bead suspension polymerization, and you may add the styrene and initiator blend consisting of a main initiator with which may have a low activation energy and the final one which may have the high activation energy. So, you may introduce this thing as well as the stabilizer just to prevent the coalescence of those polymer particles. They are injected into the reactor and the droplet size variation may occur throughout the heating period. So, you may experience the variation in the droplet size. So, when you achieve the specified polymerization temperature, the polymerization begins. So, usual polymerization temperature is around 75 to 95 degrees Celsius. So, the polymerization monomer droplet, they travel together in 3 different steps, during which the rate of drop breakage or coalescence varies continuously. So, this is a quite obvious phenomena. So, finally, clear spherical particles with a smooth surface and zero porosity are formed. You can introduce the porosity also. So, in that case you require to add some porogen agent at the appropriate quantity. Now, auto acceleration of a polymerization rate due to the gel effect is appreciable at comparatively low monomer conversion, that is sometimes about 30%, and persists until a monomer conversion of about say 95% occurs. So, where the glassy state transformation occurs and the bead become more and more strong. So, this because suspension polymerization, if you see that at startup the beads are having very low mechanical strength. So, whenever you use those beads into other further processing, sometimes these beads may not offer the desired properties. So, therefore, the mechanical strength of those beads are extremely important. So, once the beads are hard or they possess the required mechanical strength, the reaction mixture is heated to the temperature above the glass transition temperature, that is more than sometimes 100 degrees Celsius or around 95 to 100 degrees Celsius. So, if you are the polystyrene system, then it is around 95 to 100 degrees Celsius. Subsequently, you may pressurize the reactor with the nitrogen, say at around 7 to 9 bars, and that is so called the impregnation stage starts. Now, during this stage, you may diffuse the normal pentane into the beads. At the same time, the free volume increases with the finishing initiator rapidly decompose to produce free radicals, and resulting the relative increase in the monomer conversion to about say 99%. That is quite significant in nature. Now, let us have a discuss about the effect of N-pentane on free radical suspension polymerization of styrene. Now, it is observed that the presence of N-pentane, it reduces the polymerization rate due to increase of the free volume of the system, and that delayed the appearance of gel effect. So, pentene reduces the hydrogen abstraction rate from the styrene and a critical kinetic step for the transition of the chain to the monomer. So, that is the important thing. Now, let us have a look about the powder suspension polymerization. You see that in the, when we started this suspension polymerization concept, we said that there are 2 type of things can be observed in the suspension polymerization. One is the bead suspension polymerization, another one is the powder suspension polymerization. So, the powder suspension polymerization is the most important polymerization process which is being used in the production of polyvinyl chloride. Now, the key benefit of this method is that the large porous polymer particles can be produced, say in the range of 300 to 500 micrometer with a quick residual monomer removal rate and a large plasticizer absorption capability. So, the development of polymer particles with the desired PSD and the porosity, this can be accomplished by adjusting the quantity and the form of stabilizer as well as the speed of the agitator without influencing the molecular properties of the product. So, polymerization is usually done or isothermal basis. The temperature ranges between 45 to 70 degrees Celsius depending upon the target molecular weight. Again, the importance of molecular weight comes into the picture. In free radical VCM polymerization, the first polymer chain, this is we are producing one example, the first polymer chain formed within the monomer droplet are precipitated to form the unstable polymer microdomains with a diameter between 10 to 20 nanometer. Now, these microdomain demonstrate the minimal stability and aggregates to form the nucleus of the primarily particle. They are also known as a domain. So, the monomer conversion at this startup is in the range of say 0.1 to 10%. The initial stage or initial size of these domain, this lies in the range between 80 to 100 nanometer, and the growth of these domain via the polymerization of the absorbed monomer or by the aggregation of other domain result in the primarily particle with the diameter in the range of say 100 to 200 nanometer. Sometimes the critical monomer conversion is again very important. So, at critical monomer conversion, say in the range of say 10 to 30%, massive aggregation of primarily particle, this lead to the formation of 3-dimensional polymer skeleton. So, by this stage you can start observing the things to be happening. Now, the primary particle, they continue to grow until the disappearance of the free monomer phase, that is the fractional monomer conversion, sometimes referred as XF. So, the presence of secondary stabilizers at low agitation speed, the aggregation and subsequent fusion of primary particle, this can be limited with the individual primary particle may continue to grow up to the say of 1 to 1.5 micrometer in diameter. So, in that case the primarily particle can be bundled tightly together without any noticeable aggregation. You cannot, the clear cut aggregation cannot be observed in this case. So, this results the close packed structure having a low porosity particle. The porosity of PVC grain increases as sometimes the agitation rate is increased. So, strong agitation can also favor the aggregation of the individual polymerization particle. This leads to the formation of irregular PVC grains with the size range of 50 to 250 micrometer in diameter. So, you may experience the irregularity in the size structure. So, sometimes if you wish to have specific use of these PVC grains, then you need to go for meshing or sieving of those particles being generated. The main difference between the bulk and suspension process is that the agitation which is used to control not only the aggregation of the primary particle, but also the size distribution of the final grains. So, sometimes if you are having the more and more agitation, in that case you may your final grain size may become more and more finer. So, as a result of this above mechanism, the polymerization of VCM droplet sometimes they loses its viscous character at a relatively low monomer conversion, while at large monomer conversion sometimes greater than 30%, it behaves like a rigid sphere due to the presence of continuous polymer skeleton, and sometimes you may not even be in a position to process that particular thing. So, the above critical conversion, that is Xc is around 30%, the volume contraction of the polymer particle stops, and which partially you can say they explain the appearance of internal particle porosity. So, this at this particular juncture the agglomeration and the volume contraction ceases. So, that means you can say that the generation of internal particle porosity starts at this juncture. In the VCM, the suspension polymerization, there are two types of stabilizers as we talked in the previous one, that is the primary and secondary. The key function of primary surface active agent is to control the grain size, but also influence the internal grain porosity, because grain porosity is again very important in case of the processability. The other hand, if we talk about the secondary stabilizers, they are the surface active agent with the higher lipophilic content, that is sometimes polyvinyl alcohol stabilizers with low degree of hydrolysis. The improved stabilization of primarily particle, this due to the adsorbed secondary stabilizers. This results in the decrease in the rate of aggregation of the primary particles with the contaminant decrease in the porosity of PVC grains. One of the most efficient way of removal of polymerization heat is to use the overhead reflex condenser, so that you may have overhead reflex condenser, so any kind of exothermicity can be removed in due course of time. Now, this VCM vapor, they are diluted and returned to the polymerization suspension, while an equivalent volume of VCM is vaporized to preserve the thermodynamic balance, as we discussed in the previous point. So, the reflux, sometimes reflux affects the morphological properties of polymer whatever you produced in due course of time, because the morphological property is again very crucial when we talk about other application of the polymer being produced under the head of PSP. The particle size and the porosity of a PVC grains, this shows the direct proportion relation with the operation time of a condenser and reflux rate. So, these two things are supplement to each other. It is also advisable to use the reflex condenser after a monomer conversion of about 5% is reached. So, you can say this is the critical time to add the reflex condenser. Early utilization sometimes can lead to the higher condenser fouling and sometimes of a disturbed resin concept. Now, it is found that to be more safer and convenient to use the reflux when monomer conversion reaches about 20 to 30%. Now, as its effect on PSD becomes insignificant and a substantial effect on the grain porosity you can easily observe. For the case of VCM suspension polymerization, reflux can introduce some operational problems. Let us take one example, that non-condensable gases may be concentrated in the condenser, which can reduce the heat removal capacity. So, this particular approach need to be require attention. Now, the value of non-condensable gases in vapor phase side, this that depends on the quality of monomer, what kind of quality you are using, then vacuum prior to polymerization, and generation of various inert gases during the polymerization process. So, let us take the example like azo initiator, they can lead to the formation of nitrogen as a byproduct of the initiator decomposition. So, this creates significant effect within the reactor mass. Now, sometimes if we use the carbonate buffer during the process, the CO2 sometimes will form, and if the aqueous phase becomes more and more acidic in nature. So, in this particular lecture, we discuss about the various aspects of suspension polymerization. The special attention was attributed to the powder suspension polymerization. And if you have anything in your mind, then you can refer to these references which are enlisted over here. Thank you very much for paying attention.